Okay, question 2. So for question 2, we are standing in front of TJ, or sorry, Dr. Walker is standing in front of TJ, and he throws a ball straight upward with an initial speed of v naught. And so we want to know these two things in terms of v naught and g. So, of course, no problem should be attempted without a picture. And I am serious about that. It does help tremendously if you have a picture. So, because it helps you visualize what's going on, and and sort of lay out your work. So what we want to find out is how high the ball goes and how long does the ball spend in the air. So we're going to need to look at the ball when it's at the top of the peak, or sorry, the top of its arc, the peak of its arc. Top of the peak is not really. Yeah. Anyway, so we start at right here where Dr. Walker is throwing it up. So I'm going to say v1 is that's its velocity as it's at 1 is, well, actually before we can define that, we need to establish a coordinate system. So I'm going to go with up being positive y. It's a commonly done thing. And that means then that the acceleration throughout this whole thing is going to be, it's going to have a magnitude of g, but it's going to be in the negative direction, right? So there we go. So v1 is going to be positive and equal to that initial speed of v naught, okay? At 2, at the very top, the speed is going to be 0. And then at 3, so I'm going to call it v2, okay? And then at 3, v3, it's going to be coming back down. And I think it should be pretty easy to see, if you're familiar with projectile motion, that if you throw it up with an initial speed of v naught, it comes back down, or initial velocity positive v naught, it's going to come back down with a final velocity of negative v naught, okay? That may not be particularly relevant here. Let's see, will it? Probably not. Whatever. Okay, so anyway, what we'd like to do is see how high the ball goes and how long it spends in the air. So let us take, in addition to saying that positive y is up, I'm going to say that the point where the ball starts, I'm going to define that as being y equals 0. And then what we can say up here is that y equals h when the ball's at the peak of its arc. And so that just gives us something else to use besides, well, it sort of defines it for us. I'll show you in a minute. Hopefully this will make some sense when I finally get doing the problem. So let's switch to, I don't know, red. Red's always fun. So what we want to say is delta y, which is our change in y, is going to be, so let's say delta y, we want to look at, so we want to find this h, right? So delta y from 1 to 2 is going to be y at point 2 minus y at point 1, and that is going to equal h, which is our y value at point 2, minus 0, which is our y value at point 1, so that's h minus 0, which is just h. Okay, so going from 1 to 2, delta y is h because it goes up positive h. I'm sort of doing extra steps here just to be super clear and everything. We don't necessarily have to do this all the time. But looking at going from state 1 to state 2, we know v2 is 0. We know v1 is this v naught, which is considered a given. We know the acceleration is g, and we need to find this delta y. So we can, the equation that works there is v final squared minus v initial squared, and then we take 1/2 of all that, and that's going to equal a times delta y. Okay, and since we're going from 1 to 2, our final velocity is the velocity at 2, so 1/2 0 squared minus our initial is the velocity at 1, which is positive v naught, so that's going to be v naught squared, equals the acceleration we have is negative g, right? So negative g, and then h is our delta y. Okay, so what we get out here when we sort of, cancel some things is we get 1/2 v naught squared equals, and this is negative, right? So 1/2 times 0 minus v naught squared is negative 1/2 v naught squared equals negative gh. Or, what are we trying to find here? We're trying to find h, right? So this is for part A. So solving for h, we get the negatives cancel, and we get h is v naught squared over 2g. Okay, so that is for part A. Okay, and then for part B, how long does the ball spend in the air? So, part B, there are, let's see, there are probably a couple ways to do this. Are there? Well, one is if you know this part, you know, yeah, there are a couple ways. So let me see if I can scroll down just a tad. Well, okay, so how long does the ball spend in the air? If you know that it comes back down with the same speed that you're left with, just in a different direction. So v3 is negative v naught, v1 is positive v naught. Then you can take that and find what delta, come on, delta v is between state 1 and state 3. And that's going to equal your velocity at 3, which is negative v naught. Or let me just be ultra clear here. So this is going to be v3 minus v1, which is going to be negative v naught. That's our velocity at 3 right there, minus positive v naught. Okay, so that's going to equal negative 2 v naught. And then, now that we know that, we can say that the acceleration, that uniform acceleration there, is our change in velocity, 1 to 3, over the time that passes. And really, this is just, you know, this is just taking delta v equals a delta t, right? But the form we actually want to put this in, we want to solve for delta t because we know a, right? So delta t equals delta v from 1 to 3 over a, okay, which is then negative 2 v naught over negative g. So delta t, or really I would just say, you know, if we want to just say little t for time of flight, or maybe t with a little f subscript if you want. Nah, let's screw that. No f subscript. I need to stop changing my notation so fast, okay? So, or so often. So let me just back that out and go t equals 2 v naught over g. Now I hope that's legible. Let me just move down a wee tad. Okay, well, anyway, the other option would have been to look at delta y, and instead of going from, well, I've got it off the screen now, but 1 was the start, and then 2 was the peak, and then 3 was the bottom. So instead of going delta y from 1 to 2, go delta y from 1 to 3, which is 0, right? Because it begins and ends at the same position. So this displacement there, and then apply the equation that looks like v initial times delta t, okay, plus 1/2 acceleration times delta t squared, and that all equals 0, right? So what you can get out there is you can factor out a delta t because the left-hand side is 0, and it really ends up reducing down to this anyway, okay? So you get the same answer. Anyway, that's problem 2.